Hello all. In the previous tutorial we completed the coding for our IP core and we packaged it also, but we never verified it. We never checked whether it is working properly or not. So we have to do simulation. So for all the coding that we have done till this point, we did simulation just by forcing the signal in the waveform window. So for this IP core, that's not going to work, because if you really want to check whether it is working, you'll have to really send a image and check whether the output is coming properly or not, and that you won't be able to do using waveform forcing. So we'll have to write a proper test bench in this case. So let's go ahead and write the test bench. Now the test bench I am trying to write is the minimal test bench. I'm not going the proper coding methodology for test benches, because at this point of time my only aim is to check whether my IP is working or not. Maybe we'll make a different tutorial on Verilog where we can discuss the different verification methodology, what are the proper way of writing test benches, things like that. Okay, so today I'm just writing a manual test bench which will actually read a image and send it to our IP, and it will receive the data coming from the IP, and you will be able to see the actual output. Okay, so start as a new source and we'll choose this option, simulation source, because if you choose that option, Vivado will automatically find like this module. It's only for simulation, so he will never use it for implementation. So let's call it tb.v. And I guess you understand test benches. They represent the external world for the piece of hardware that we are simulating. So it is supposed to give all the signals coming from the external world as well as accepting all the signals coming from our hardware. Now, when you write test benches, you have more flexibility because you are not aiming to synthesize it. You are not aiming to really implement it in hardware in most of the cases. So you have more flexibility. So we will see. You can write more programming constructs, like you can write for or while loops, things like that, the same way you write it in C programming or other high-level programming. So as I mentioned, so in Vivado, once you choose this is a simulation source, it will never come under design source, it will just come under simulation sources. So here our test bench is sitting, and we can go ahead and open it and can start. And again, test benches, they represent the external world of our hardware. So the test benches, it won't be getting any signal from the outside, or it won't be sending any signal to the output outside world. So its port declaration will always remain empty. First thing what we'll do is we'll just go ahead and instantiate our hardware inside our test bench. Okay, so this is our image processing top. So let's call it, usually we call it DUT, the instance name, design under test. And let's try to do some port mapping. Okay, so first thing we obviously need is a clock. So let's try to create a clock, and this is one way you can create clock signal. So you can initial, okay, we'll make a signal called clock, and let's initially make it say 1 tick be 0. Then we can write an infinite always block for our block. Okay, begin end. You can say clock is not of clock. You can either use this one or you can use the tilde, both are fine. Clock is not clock, and it should happen after every 5 unit of time. Now when I write 5 here, what is the unit is defined by the time scale. Here we have nanosecond. That means after every 5 nanosecond you want to make clock equal to not clock. So this will effectively make a square wave which has a period of 10 nanoseconds, because you are toggling after every 5 nanoseconds, right? So that's it. So that's our clock signal. We can end, and we can declare it reg clock, and we can just connect that clock here. Okay, now usually again when we start, initially we need to apply a reset signal to our hardware, wait for some time, remove the reset, then start giving the signal. Okay, so initial begin end, so we'll have a reset signal. Again we are following axis stream, so reset is active low, so let's keep reset low and wait for 100 nanosecond, and then remove the reset, and again wait for 100 nanosecond. After that we'll start processing. So let's declare reset also, reset, and let's connect it here. Now if you are using Zynq IP cores, okay, always keep, again you can use the same test bench for post synthesis simulation also, okay, after synthesis also. So at least always keep 100 nanosecond for reset, because Zynq IP cores, they internally expect minimum duration for reset, and in real world also Zynq, they have a some kind of internal reset called the global set reset signal that will be active for 100 nanoseconds. So in real world the FPGA will be automatically applying a reset signal for like 100 nanoseconds. So keep at least 100 nanosecond for reset. Anything more than that is also fine, so keep it asserted for 100 nanosecond. Next, okay, we can send data. So this time I'm really going to send an image. As I mentioned before, we'll be using Lena herself. Okay, so the code will look very similar to your C code. Okay, so we'll be opening that file, reading 1 byte at a time from the file, then we'll be injecting it to our DOT. So this is how we open and close files in Verilog, similar to our C. File is equal to, but here it is like $fopen. Okay, you have this $sign, which is indicating this is either a system task or so-called system function. So $fopen, it is a function. It will return a pointer, and that pointer will be of integer type. So, and followed by the file name. Okay, so we are going to use the same file, lenagray.bmp. Okay, and we are opening it into read mode. It's a binary file, so you need to type lenagray.bmp read in binary format. Okay, keep it in mind. Fine, so we open the file. Next we can start sending data from the file. Now remember, this file, it has a header part also, right? It has a header part also, but our IP core, it is going to process only the pixel values. Okay, so the header part of this image file you should not send. So that initial part you need to skip. You need to just read it from the file and just discard it. Okay, so for I equal to 0, now how many bytes are there in the header? If you remember, it is 438 hexadecimal. This is Verilog, so we have tick define instead of hash define. 1080 in decimal. Okay, so this is the header size. So what I'm doing is I'm just reading that data. I less than header size, I equal to I plus 1, I equal to I plus 1. Okay, I'm going to read byte by byte. So we have the system function, yeah, fscanf. The syntax is fscanf, the pointer to the file, what you want to read. I want to read 1 byte at a time, so we can use %c followed by where you want to store that data. Okay, so let's call it some image data or something. Okay, but it's the header part, of course. So what I'm trying to do is I'll be reading from this file, and at the end I will need to see the output image after processing. Now again, remember, I'm sending only pixel part to my IP. He will process it and he will give me back the pixel part. Now if you really want to open that file and see it as an image in Windows, that output file should also have the header part. Okay, so but the header part remains same for your input image as well as the process image, because all the information is same, like what is the file size, what is the resolution, what color coding is used, all those information are same. So what I can do is I can read from my input file, and I can just write to an output file. Now later, the processed pixels I will append to that output file, so that later I can open that file and see it in Windows. So we need to open one more file. So let's call it file1, and let's say $fopen, and let's call it maybe blurred lena.pmp, and we are opening it in the write mode. Okay, it's a binary file. So I will read the header 1 byte at a time, and I will just write that. So f, it's not f printf, it's f write here. Okay, $f write, file formatting again %c, and let's say image data. We need to declare it image data. It's a 8-bit data, so we can say reg 7.0 image data. Okay, so we need to declare these file1 also. The point is they should be declared integer type, file and file1. Okay, let's see. Okay, so he's happy. Again, Verilog with the tick define, you need to write here tick header size, not just header size. Okay, so once we do this much, he should be happy. I also need to declare. Okay, let's declare I also. So you'll see like this is more like software coding now. Okay, so I finished reading the header part. I copied the header part to my output file. Next, we will send the actual pixel data to my IP. Okay, so what I'm going to do is, in real world also, this is what we do. We have 4 line buffers inside our IP. So I can read 4 lines from the image and directly send it to my IP. Okay, so I'm going to read 4 lines and I just send them to the IP. I cannot send the 5th line because I don't have any free line to send the 5th line. I will send the 5th line when the IP will say he's ready to accept the next line. How he will tell me? Through the interrupt signal. Okay, so let's go ahead and read the 4 lines. Okay, so for I equals 0, I less than 1 line is 512, so 4 times 512, I equal to I plus 1. So the code looks similar to the previous one itself. We will do this one, fscan of image data. And we need to give it to the IP. So how do we give it to the IP? I will give it to the IP by asserting the valid signal to the IP. Make sense? Yeah. So we'll say we will read it, and on the next positive edge of the clock, because we have a synchronous system, so we need to wait till the next positive edge. Okay, so we are waiting till the next positive edge. Then we will say image data valid is 1. So where this should be connected? This should be connected to iData valid, and this image data should be connected to iData. Now this image data is not going to the IP because my image data valid won't be asserted. So at the beginning itself, let me make it 0. Let's declare it reg image data valid. It's better we read it on the clock edge. Okay, so on the after the clock edge, we read from the file and make the valid data high. Okay, so once we send 4 lines, what we need to do, we need to wait for the interrupt signal, because that interrupt signal is telling me there is a free line available now to send the next line of data. So I will deassert this valid signal because I'm not going to send any data until I get the interrupt. So we need to wait until the interrupt. When you get an interrupt, you send the next line. Again, wait for the interrupt. When you get an interrupt, you send the next line. So how long you should send like that? You should send like that until you send the entire image to your IP. Okay, so that I can write something like this. So let's say while we have some variable which tells me how much data I have sent till now. So let's say like send size or something, and maybe at the beginning we will say send size is 0. Now we are not worried about what is the exact width and all here because it's a test bench. We are not going to implement it. So we are not worried about resource utilization. So send size, let's initialize to 0. And once I send this much data, that means I have sent, okay, 4 times 5. I have sent that much data. Now, while send size is less than the total image size. So let's declare it here. Define image size is 512 times 512, right? That's the image size. So while send size is less than image size, see, you can use while loop and all, just like C code. What you will do is you will wait for the interrupt. Okay, so we are doing an edge sensitive interrupting. So I am just waiting for the interrupt signal to come. So this basically means wait for a rising edge of interrupt. So this interrupt, we'll connect it here and we'll declare it. It's an output, so it should be while. You wait for an interrupt, and once you get an interrupt, you will send next line of data. Okay, so how do you send next line? For similar code. So for this much, but you are sending only one line. So I equal to 0, I less than 512, begin end, and on the next positive clock edge, you will read from the file the next pixel value, and you will also make the signal high. And once you finish sending one full line, on the next column positive edge, you will make the valid signal 0. So you should change all these signals only after a positive edge of the clock, because then only it becomes synchronous. If you do it without this positive edge, what happens is your image data will be high, and immediately after you come out of the loop, image data will become low on the same clock edge. So your IP won't be seeing like this valid signal high for one clock cycle. So you should do it something like that. Okay, so this signal, did we connect it? Yes, we have connected. Now this ready signal, I'm not looking at this ready because I assume my IP is always ready to accept data. Okay, to keep things simple, how will I make sure my IP is always ready to accept data? By making sure I am always ready to accept the data given by him. So remember, we have a FIFO inside which is controlling this ready signal. So as long as we tell the FIFO I am ready to accept data from you, he will not make this signal low. It will be always high. Fine. So we send all the image data, and we need to increment the send size by 512. By the time we come out of this loop, we have sent all the image data. Now remember the first thing we discussed. Now what I did was I copied the entire header from my input file to the output file. Okay, so the output file size we are expecting it to be same as the input file size. But remember I discussed when you do convolution, you are doing like this, right? So we are going like this, going like this, going like this. There will be an issue of dimensionality reduction. Okay, there will be one row missing at the top and one row missing at the bottom. Similarly, column wise also you will be missing two columns here, but in our implementation that issue won't come. Okay, that we'll discuss later. But row wise we will have that issue. So I am sending first 4 lines, so he's doing convolution like this. So effectively we are finding pixels corresponding starting this second row, and final convolution will be happening somewhere here. So we'll be finding the output corresponding to this row. So there is a convolution missing for this row as well as this row. So because of that, there will be a dimensionality reduction. Now to overcome it, we will be sending 2 dummy lines. So that 2 dummy lines, maybe one line you can send before and one line you can send after. In our case, maybe it is better to send 2 dummy lines towards the end, because at the beginning I am sending 4 lines blindly, right? So you will see like there may be some slight shifting in the image because of this sending the dummy line. But without those dummy lines, the output image size will be less than the input image size. And since we are using the same header, you won't be able to open it in Windows. So to avoid it, let me send 2 dummy lines also. So same way, once I come out of this loop, I will make this 0. Okay, then I will send 2 dummy lines. Okay, so we can use this one. So we'll wait for an interrupt, post search reset. Oh, sorry. We'll wait for interrupt intr, and we will send 1 line. There is nothing to read from the file, so we will just say, you can just say image data is 0 because the file is already empty. Now once we send first line, again we can wait for next interrupt, and we can again send 1 more line. Okay, after that we can make the data value 0. Okay, so it's a good idea, once you have used a file, close it before exiting the simulation. $F close and the file point. Okay, so that's it. So the writing part is only this much. Now we need to write the logic which accepts data from our IP and write it to the output file. Okay, so the header part of the output file we have already written. Now we need to write the pixel part of it. Okay, so how can we do it? We will just check whether any valid data is coming. Okay, so let's say like out data valid here. We'll just check whether if the signal is high. If the signal is high means there is a valid output data. Out data, let's call it like that. And whenever it comes, we will write it to the output file. Output file is file1. That is the pointer. So similar to this, we'll say file1 %c out data. So let's declare them. Data is 8-bit. It's output, so wire. And we also have data valid. Okay, so how do we know like whether we have finished? Okay, so for that we can use another counter which will basically increment each time we receive a new data, and whenever we receive all 512 by 512 data we can stop simulation. So we'll say integer received data and let's initialize to 0, and whenever we get a data here, and if received data is our image size, that means we received all the data, we can close this output file. You should close the output file so that all data is updated there. File1, and you can stop the simulation, $stop. So this will just stop the simulation, but the waveform will be still there. If you write $finish, you will exit from the simulator also. But so better keep $stop. So that's it. So that completes our simple test bench. So you might have noticed our code looks more like software programming. So Verilog as a programming language, it is also a Turing complete programming language. So basically anything your C program can do, Verilog can also do. Okay, it's as good as C in theoretical point. But whether it will be efficient the same way as C is a different question. But it can also do file manipulation and input output control and all looping, all if else if everything it can also do when it is seen as a programming language. Okay, so that's it. Now we can go ahead and simulate and see. So we need to go to settings, and under simulation we need to make sure the simulation top module name is TB. It is already TB, and when you try to simulate, we can go to here. You are getting an error here. A lot of error is actually coming. So it's basically saying line 62 file pointer, file descriptor is not valid. Okay, so he is basically unable to open our file. So this Lena, he is not able to find actually. Because if you write like this, the assumption is this file is available in the current working directory or current simulation folder. So you'll see the warning here, file Lenagre BMP could not be opened. So where you should keep this file, you can actually keep the file wherever you want. In that case, you will have to give the full path to this file. But if you are writing like this, where the assumption is the file is in your current simulation folder, what you should do is you should copy this file to that location. So we are in Vivado image processing You go there, there is a sim folder. Under that sim1 behavioral xsim. This is the current simulation directory, so you should keep it here. Okay, so let's clear all output. Let's restart simulation and let's run it. Okay, so here there is an error like 63. Yeah, so we made a mistake. Here we need to write file 1. We are reading from file, writing to file 1. Okay. So again, so we changed the code, so we need to relaunch simulation this time. We need to recompile. And let's run. This time no errors are coming. We can see the waveform actually. And it actually stopped. Yeah, you can see in the waveform how data is going and where the data is coming. Okay, so this is where image data, this is the data we are sending. Looks fine. This is our image data valid signal, so this is where we are sending data. 3B38 looks fine. And out valid, okay, this is where we getting data. Okay, so there is some latency, so remember we have the line buffers. Only after filling the line buffer we will start getting output data. And here you can see interrupts are coming, so in between where interrupts are coming there is some break here, right? Only after getting the interrupt we will send the next line. Okay, so we can go and check the output. Okay, so here is the output, blurred.lina.bmp, and you open it. Okay, so if you remember the output from MATLAB, it is looking exactly same. This is the original and this is the blurred, so you can see some blurring effect is there. Now, as I mentioned before, there is a slight shifting. Okay, so it seems like there is some additional row at the top and an additional column at the right. That's what happened. Now we send the dummy line towards the end, but it seems like the additional row came on the top. Okay, so let me just give a clue. In a BMP image, the first pixel, okay, inside that file is actually representing the bottom left pixel. So data is stored like this. It is not stored like this in the BMP image. Okay, so I guess based on that you can find out how the shifting is coming at the top. Now towards the right one, what is actually happening? So when we wrote our line buffer, we didn't care like what happens when we are reading from this position. We always read from some pixel position and we send that pixel and the next two consecutive pixels. That's how we wrote it, remember? So if you look at your line buffer, we set like our out data is read pointer 1, read pointer 2. Okay, so what happens when we are here? He will send this, this, and this. And what happens when he is here? Read pointer plus 1 and read pointer plus 2. Because of the read pointer size is 9, it will automatically offer to 0. So you are sending this, this, and this. And when you are sending this pixel, you are sending this, this, and this. So that's why you don't have to explicitly worry about the width of the image changing, because that is automatically taken care. Instead of having dummy columns, you are actually sending this one and these two when you are reading from these last two pixels. Okay, Yeah, so that's it. So it seems like our IP is working perfectly. Maybe I would like to show one more thing. What is the advantage of having our 4-line buffer? What happens if we don't have 4-line buffer? So notice here how much time we took for entire processing, approximately 2.64 millisecond. That is the total time taken. Now assume we didn't have that 4-line buffer, we had only 3-line buffer. How your code will change? If you have only 3-line buffer, at the beginning, okay, at the beginning you cannot send 4. At the beginning you can send only 3 because you have only 3-line buffer. So you will send 3, send size will increment by 3 times 512, and this part remains same because we are directly taking image size. Okay, so this is how it will look like. Close the output. 2.64. Okay, so let me recompile. And let's run again. If you check the output, still the same. So everything is still working. But the problem is the time taken is 5.2, which is approximately double of the previous time. So if you see your image data value, how it is going, see, previously it was consecutive, but now it is like he will send line buffer, 1-line buffer data. So at the beginning he sent 3 together. See here, he sent 3. Then he is waiting for the interrupt to come. Till that he is not sending. Now interrupt came, he sent 1 line. Okay, so only after we send this line, the internal convolution is happening. So that is happening during this much time, and during this much time he cannot send because there is no interrupt. So after that time interrupt comes, he sends the next one. So this is more like sequential, and because of that we have big performance penalty. That's why we added that 4th-line buffer. Now if you ask whether there will be improvement if you again increase the number of line buffers, yes, it is possible. Sometimes you may get some little bit more timing improvement, but not a drastic one. So bare minimum, you need to keep height of the kernel plus 1. That many line buffers you should keep inside your hardware. Okay, so I guess now you have some idea about our simulation. So in next tutorial, we will build a system, complete system, and integrate our IP core with the Zynq processor. Thank you.